Okay, so we are almost done with this unit. And this video is mostly going to be just giving you example problems using a tool that I said we would learn in the last video to do some integration. And this is going to help us do more complicated integrals. And this technique is called U-substitution. Now, let's say we have two functions that are multiplied together. So we have 2x squared times this 3x cubed minus 5 to the 20th. How can we integrate that? We don't have a rule that lets us split integrals by multiplication, but I'm looking at this, and if I'm thinking about stuff as an antiderivative, well, I'm looking at this function right here, this inside function, 3x cubed minus 5. What happens if I differentiate that? Well, it gives me 2x squared. So let's actually do something with that. If we notice that something is the derivative of something else, that gives us allows us to use a powerful tool called U-substitution, where I'm just going to actually say that U equals 3x cubed minus 5. I'm trying to get it to load. Hold on. Okay, hopefully that fixed it. And then, like I said, well, if we take the derivative of this, so if we say du, the derivative of u, with respect to x, I'm just not writing that dx anymore, is equal to 9x squared and this isn't exactly the same, but it's close. Oh, and I missed something. Dx. I want to write the dx this time because writing this dx allows me to substitute in to here, but I'm just going to do one final step. And we're not going to do this all the time, but in this case, to me, it makes sense. So I'm going to do it. So du over 9x squared equals dx. I'm just solving for dx. And now let's substitute all this stuff in. So this dx, I'm going to, well, yeah, it's going to, no, I'll write it in the proper order and then we'll rearrange the order. So this 2x squared is going to stay there. Then we have this 3x cubed minus 5. I'm going to replace that with a u. So we get u to the 20th, because we solve this power of 20, and then dx is going to become du over 9x squared. And let's rearrange this to make this look a little prettier. We get the integral. All I'm going to rearrange is I'm taking this 9x squared and I'm going to move it, or dividing by 9x squared and move it over here because this is all effectively multiplication. So we're going to have 2x squared divided by 9x squared times u to the 20th du. And I'm going to save myself a line because it's going to run out of space. But this x squared over x squared, that's just going to simplify to 1. It's going to go away. And now I just have the integral of u to the 2 over 9 times u to the 20th. Well, this is just our integral power rule. What am I going to do? Well, I'm going to take this exponent, add 1 to it. So we're going to have u to the 21. So we have 2 over 9. And dividing by our new 1, dividing by 21, and that plus c. And there's our integral. Actually, I'm going to write one more line just to make it look prettier. To simplify this, I would just do what's 9 times 21. 189. So we get 2 over 189 u to the 21 plus c. And in this case, I'm actually going to do one more. When we get to definite integrals, you won't have to do this next step. But let's rewrite it again in terms of x, because we started with x, so let's end with an x. So this is going to be 2 over 189, and our function was, our u was 3x squared minus 5. 3x squared minus 5 to the 21 plus c. So we're actually doing a lot of just algebra here. And this is our antiderivative. And if you even think about it, if we take the derivative of this, will it get us to that? Well, I am going to get a 3x squared minus 5 to the 20. So that covers this part here. And then multiplying by the inside of this times, or the derivative of the inside of this times 9x. Oh, did I miss something? Is this supposed to be... Oh, this squared is supposed to be a cubed. There we go, that fixes it. And then our derivative of the inside would be 9x squared minus 5, or 9x, just 9x squared, sorry. So we would multiply this by 9. If I multiply this by 9, well, it takes me back to 21. And then I'm also multiplying by 21, so that goes away, and we're just left with the 2. You can take the derivative if you don't trust me. All right, next one. And this one I'm going to show us another way we can use sub. So this is a trig function. We have this inside here, 3x. What is the derivative of 3x? Well, that's 3, so that's going to tell me that I probably want to use my chain rule. So we'll say u equals 3x, and then du equals 3dx. And here I actually noticed something. I'm going to rewrite my integral to make it a little more apparent. But we have cosine of 3x times 3dx. For this integral, we actually have it already set up perfectly to substitute, because this 3, I'm just going to move it back here to put it next to the dx, and suddenly we have 3dx equals du. So now I'm just going to substitute that in. I'm not going to actually solve for dx when I don't have to. You could if you wanted to, but... So we're going to rewrite this as cosine of u du. And this is one of the problems I did yesterday, by the way, except now I'm giving you the tool. And now what is the integral of cosine? The antiderivative of cosine, well, that's sine of u plus c. And then we're just going to substitute our 3x back in for u, so we can rewrite it in terms of x. So it's sine of 3x plus c. Boom. And there's our antiderivative. And if we take the derivative of this, does it give us that? Well, the derivative of sine 3x is cosine 3x times the derivative of 3x, which is 3 cosine 3x. Boom. Next one, negative 3 secant 3x tangent 3x dx. This is again something we did yesterday, but now we have our u sub. Well, here again we can see the derivative of 3x would be 3. So let's try doing that. U equals 3x. Then du equals 3 dx. And I'll rewrite my integral to make it look a little prettier. And I'm actually going to use one of my derivative rules. I'm going to take this negative and I'm going to pull it out. I'm going to put it at the front. So we have negative, and I'll go ahead and put in the u's. Secant of u, tangent u, times 3 dx. And then I have a 3 dx, I can just replace that with du. So I'm not even going to save the line, you see it there. That's going to become a du. And we take the integral of this, well, the antiderivative of secant u tangent u is secant, sorry. So this is going to end up being negative, because I have this negative out front, negative secant of u plus c. And finally, replacing our u with our x again, negative secant of 3x plus c. Boom. Another example, we have two more just with indefinite integrals, and we're going to talk about definite integrals and change of bounds. But really quickly, we have tangent of 3x dx. This one's a little bit trickier because I don't see anything that's a derivative of something else. So let's try rewriting this. And also, I don't know what the derivative of tangent, or the antiderivative of tangent is. Let's try rewriting it as sine of 3x divided by cosine of 3x. And now I'm here, and I can look at this two ways. I can say the derivative of sine is cosine, the derivative of cosine is negative sine, so this time we're looking at our sine and cosine instead of the 3x, and which one should we use here? And I actually think it doesn't matter which one you use. I'm thinking about it. No, it does matter. It doesn't matter which one you use. Okay. So this one you're gonna kind of have to get an eye for which one to use. I'm gonna do both of them and then sort of show you why one works and one doesn't work. Let's start with the cosine. So let's say u equals cosine. No, I'm sorry, I don't want to start with cosine. I want to start with sine. U equals sine of 3x. Du equals 3 cosine of 3x dx. Okay, and this doesn't line up nicely with our dx. We don't have this nicely in our thing, so we can actually solve for dx here because it doesn't line up nicely. So I'm going to say du over 3 cosine of 3x equals dx. Just like we did on that first example, since it doesn't line up nicely, let's try this. And then let's substitute in. So we're going to get the integral of u divided by cosine of 3x times du over 3 cosine of 3x. And here we get kind of stuck. We can rewrite this as u divided by 3 cosine squared of 3x. And you could actually do something with that if you really wanted to keep going down this path. But I think for most people that would just be confusing. What we would actually have to do is we'd have to do another U-substitution. But I don't want to do that because this is getting a little icky. So let's back up. And instead of doing u as sine of 3x, well, let's try our u as cosine of 3x and see what happens. Oh, I probably should have given a warning that I said I was going to erase all that so that people writing it down wouldn't stick with it. If anyone can actually solve that integral doing it that way, I'd be really impressed. I might even be willing to give bonus points if you're able to integrate that and explain it, why that would work. Okay, and then our derivative is going to be negative 3 sine of 3x dx. And again, we don't have it perfectly, but we do have this sine of 3x times dx. So I'm actually only going to get rid of this negative 3 here. I'm going to work smarter, not harder. So I'm going to say du divided by negative 3 equals sine of 3x dx. So I'm trying to turn this into something that I can just put into my function. If it doesn't work, we solve for the whole thing. You can actually always solve for the whole thing and it'll work out. But so this integral is going to become this sine of 3x dx is just going to become du over negative 3. And then I'm going to end up with 1 over u, because my cosine of 3x just became u. And let's make this look a little prettier. This negative 3 is just a constant. I'm going to pull it to the front. Something to be careful of, this negative 3 is it being divided. So if you pull it to the front, make sure that when you pull it out, it's negative 1 over 3. This is not just a negative 3, it's a negative 1 over 3. And then we get 1 over u du. And the integral of this is one of our specific integral rules. This is the natural log of the absolute value of u. So we get negative 1 over 3 natural log absolute value of u plus c equals, and now just substitute back in for my substitute back in for u. That was cosine of 3x plus c. And this is our final answer. Negative 1 over 3, the natural log of the absolute value of cosine of 3x plus c. Okay, last one for definite integrals. We have e to the square root of x divided by the square root of x. This one's a little bit trickier to explain why we're doing it. Or it's a little bit harder to see. But the derivative of the square root of x is 1 over the square root of x. That's just using our power rule. So this is the derivative of that. It's a little bit harder to see there, but we'll work through it. And I think if you just trust me, if we say that u equals the square root of x, then du equals 1 over the square root of x dx. That's actually 1 over 2 square root of x dx. And now we're really close to this being the same. I just have this extra 2 because this is a 1 over square root of x. This is our dx. I just need to get this 2 over there. So we end up with 2 du equals 1 over square root of x dx. And now I can just substitute in. We get the integral of 2e to the u du, because this 1 over the square root of x dx turned into du, and I just put the 2 in front. And the antiderivative of e to the u is just e to the u, so I end up with 2 e to the u plus c. Finally, substituting in our x again, we get 2 e to the square root of x plus c. This is something, when you really start thinking about this as antiderivatives, you can always use this U-substitution technique, but I will say, like, eventually as I practiced this a lot and got really familiar with it, I was able to, you can eventually start doing this in your head, is all I'm trying to say there. Okay, and now I want to connect this to when we did our last video, when you talked about integration, I said every antiderivative rule comes from a derivative rule. Well, what rule would this be analogous to? Because we are using a rule here. And if you looked at what I have below, you might have spoiler alerted it. But if we come back up here, remember I said I was looking at this and I said this 2x squared looks awfully a lot like the derivative of this 3x cubed minus 5. It doesn't look exactly the same, but it looks awfully a lot like it. And I specifically called this our inside function. So let me reframe that, and then I'll let you pause and think about what it's going to be. We have our inside function, our function, the derivative of our function, with our inside times the derivative of our inside function. So we have the derivative of our outside function times the derivative of our inside function. Pause the video and make a guess. What derivative rule does that sound like? Maybe this notation will help you. We have the derivative of our outside function times the derivative of our inside function. If you guessed it, if you guessed chain rule, you'd be absolutely correct. This is just our analogous integral rule for the chain rule. This is our chain rule for integrals. And now coming down here, we did a ton of indefinite integrals, pretty straightforward. Now I want to talk about definite integrals. So if we're doing our integral chain rule from a to b, and I'm going to sort of walk you through my substitution here. This is kind of my notes to help me keep myself on track. If we let u be g of x, and du equals g prime of x, so this is going to become our integral from a to b of f of u du. But there's an issue here. Now that we're doing a definite integral, well, these bounds are x values. These bounds, x equals a, x equals b. But our thing is in terms of u now. So what can we do to make this a little more straightforward? Let me actually even continue writing that. X equals a, x equals b. How can we rewrite this in terms of u? Well, if x equals a and u equals g of x, well, let's just both of these sides apply this function to it. So g of x equals g of a. Actually, I will write that. G of x equals, for one of them, equals g of a. Applying the function to both sides, which is something we can do. And then what is g of x? Well, g of x is just u. So u equals g of a, and a similar thing happens here. So we can rewrite our bounds of integration from as g of a to g of b, f of u to u. And this is u equals for both. When we do this, I think it'll. I was really confused with this when I first learned this bounds of integration thing. I actually avoided rewriting the bounds of integration because I didn't understand it. And I'll show you what I did. And you can choose either way, but I am going to tell you there are going to be AP questions that ask you to rewrite this integral or find an integral that's equivalent, and you have to change the bounds of integration. So you can run away from it like I did. I'll show you how to run away from it. But there are going to be questions, so I do recommend that you try to understand it. And hopefully this makes it clear why these bounds are changing like this. Okay, but now let's do some examples. We have the integral from 0 to 5 of 3x times e to the 4x squared minus 1. Well, I'm looking at this 4x squared minus 1. That, if I take the derivative of this, it looks like 3x. And when I say it looks like, let me be more specific what I mean. What I mean is, I'm going to end up with, the derivative of this is x. At its heart, it is x. Because I'm taking away 1 from the exponent. All this other stuff is kind of fluff, but this derivative of this looks like x. And this looks like x, if I take away all the fluff. That's what I mean when I say this derivative kind of looks like that. If I take away all the fluff, does it look the same? So we have u equals 4x squared minus 1. Then du equals 8x dx. And see, this is what I mean. This, when I take the derivative is just 8x. And if I take away the fluff, if I take away the 8, I'm just left with x. If I take away this 3 from this x, all I'm left with is x. Like, I take away the fluff, and it looks similar. And we'll... I could solve all the way for dx, but I think here I'm actually just gonna just make it look nice for what I want. And I just want an x dx. It'll load. So we get du over 8 equals x dx. There's my x, there's my dx. So I'm gonna end up with, this is the integral from, now I'm gonna go ahead and write this x equals 0 so I don't forget that my bounds of integration are in terms of x right now. And rewrite it like this. So if I write x equals 0 on the bottom, it's implied that the 5 is also an x. By the way, it'd be really unnatural and sort of blasphemous to have a bounds of integration where one is in terms of one variable, the other is in terms of a different variable. And you don't denote that at the very least. Okay. But now, how are we going to get our bounds of integration? Well, u equals g of x. G of x is this 4x squared minus 1. So I just want to find what is, I'll even write this here, g of x, just for our own sort of understanding. And then I can rewrite it as g of 0 equals 4 times 0 squared minus 1, and g of 5 equals 4 times 5 squared minus 1 equals and this is just going to go to -1. 5 squared 25 times 4 100 minus 199. And we get that our new bounds would be from u equals -1 to 99, 3 over 8 e to the u du. And if you're looking at that and you're thinking, those are really big numbers, this is part of the reason why changing the bounds scared me. But let's go through and do it, and then I'll show you an alternate way that you can do this if you really don't want to change the bounds of integration. The derivative, the antiderivative of e to the u is just e to the u, so we get 3 over 8 e to the u. And here, I'm going to introduce you to another notation. Because what do we use to take definite integrals? We use the fundamental theorem of calculus that says that it is equal to this is our derivative. It's equal to our function value at 99 minus our function value at -1. The notation that we can use to write that, so this is our integral. And to say that we still need to evaluate it by these bounds, you draw a vertical line and go -1 to 99. This is the same thing as saying we're doing 3 over 8 times e to the 99 minus 3 over 8 times e to the -1. And boom, we get that. And actually, I'm going to leave it like that. That's going to be our final answer. I'm trying to think if there's something else I want to say. There's one other thing I could say, but I don't really want to say it. I suspect people will ask me in class, and I'll save my answer for in class. But there's something I didn't do here, and I'm not doing it on purpose. It's not that I'm forgetting it. But if you're kind of yelling or wondering why didn't I do this thing, you can put a comment on the video and I'll answer the comment. But I'm not going to say it in this video. I'm just going to say, the thing that I'm missing from here, I'm missing on purpose, and I'm not supposed to have it. And that's all I'm going to say about that for now. Okay. So now here, I said I would show this another way if we don't want to change the bounds of integration. Well, here's the other thing that we can do. And here, changing the bounds of integration actually worked out nicely. It looks better like this than it's going to turn out. But if I integrate this, I get 3 over 8 e to the u from x equals 0 to 5. So our first steps are still the same, except now my bounds are x equals. Well, let's substitute this u back in for x like we did with all our indefinite integrals. So let's say this is 3 over 8 e to the 4x squared minus 1 from 0 to 5. And now that I've rewrote it in terms of x, I'm not going to write the x equals anymore, because since this variable is x, it's implied that these are in terms of x. And now we'll just substitute in. So this equals 3 over 8 e to the 4 times 5 squared minus 1 minus 3 over 8 e to the 4 times 0 squared minus 1. And if you'll notice something, when it loads, this 4 times 5 squared minus 1, 4 0 squared minus 1, we already did that. That was this part over here when we changed our bounds of integration. And so 4 times 5 squared minus 1 is 99. This is just going to become this one up here, 3 over 8 e to the 99. This is just going to become negative 1 minus 3 over 8 e to the negative 1. And we end up getting the same thing. So changing the bounds of integration, this should, it's not a proof, but it should show that the bounds of integration are the same, and this works. I'll leave whichever way you want to do, you can do it that way. If you want to rewrite it in terms of x, feel free to do that. If you want to change the bounds of integration, go for that. But I am telling you there are going to be questions on both on our tests and our quizzes where I ask you to find and write an equivalent one, and I'm expecting you to change the bounds of integration, because on the AP test there will be questions like that. Okay, last three, I'll let you kind of go through these on your own, because our video is really long and I don't want to talk through all of these completely. So go ahead, pause the video, try this on your own. When I come back, I'm going to have these answers already worked out, and I'll talk us through them, but I'm not going to talk and write at the same time. Okay, I actually am going to come back really quickly before I finish working all this out and show you what I did for this first one, because we haven't done an example like this one. But if I take this, I don't see anything that's a derivative of something else here, but this looks similar to me, like almost like 1 over x. And if we take out all the fluff, that's what it is. It's 1 over x. So I'm trying to make it look more like that. And if you see here, I did u equals 3x plus 1, d equals 3x. And when I rearrange and put that in, we get 2 over 3 times 1 over u. This is like 1 over x, and this is one of our rules. We actually did it earlier. Okay, now I'll pause and I'll let you keep working. Okay, so for our first one, I already talked us through this first part here. Then I integrated. This is just 2/3 times 1 over u. The antiderivative of 1 over u is the natural log of the absolute value of u. And then I changed my bounds of integration by substituting in these x values into our u function. 3 times 1 plus 1 is 4. 3 times 5 plus 1 is 16. So we're integrating from 4 to 16. And then I just used the the first fundamental theorem of calculus, substitute that in, and I get this. I'm not simplifying any further than that. I could, technically, but I'm not going to. And this is just our final answer. Okay, for our second one, we have tangent x times secant squared x. Well, one of these is the derivative of the other. Secant squared is the derivative of tangent. Tangent is the antiderivative of secant squared. So I'm setting my u equal to tangent x. The derivative of that is secant squared x dx. And now I can just replace this whole piece with du. So I end up with the integral from 0 to x equals 0 to pi over 4 of u times du. Changing my bounds of integration. Tangent of 0 is 0. Tangent of pi over 4 is 1. So our bounds are from 0 to 1. And this one, we might have struggled a little bit this one. This is just our power rule. So add 1 to the exponent, so it becomes u squared, and then divide by our new exponent, so 1 over 2. General rule, when I write my integrals, I haven't been doing it, but moving forward I probably am, because this is the natural way for me to work it out, is I put the fraction in the front as a coefficient instead of saying u squared divided by 2. It's the same thing, but to me, I prefer the way the fractions look. That's probably how I'm going to write it moving forward. Okay, and then just substituting in 1/2 times 1 squared minus 1/2 times 0 squared, that just gives us 1/2. And so our integral here is 1/2. And when I come back, I'll have the last one. Okay. And so here, this one was a little tricky to see which one we're trying to use sub, but I know the derivative of natural log is 1 over its argument, x minus 1, and I have a 1 over x minus 1. So I took this 1 over x minus 1 is the antiderivative of natural log of x minus 1. So I substituted it, u subbed, u equals natural log of x minus 1. Take the derivative of that, du equals 1 over x minus 1 dx. And I have a 1 over x minus 1, and I have a dx, so I can just use that to get du. And then we get u squared, because I have this squared here, times du. Still, I kept my bounds of integration, and then I changed them here. The natural log of 2 minus 1 is the natural log of 1. The natural log of 1 is 0. And then the natural log of 4 minus 1 is just the natural log of 3. I don't have a calculator here, so I'm just leaving it as natural log of 3. And then using our first fundamental theorem of calculus, substitute these in and subtract them. So 1/3 times the natural log of 3 cubed minus 1/3 times 0 cubed. And that's just equal to 1/3 times the natural log of 3 cubed, because this whole term goes to 0. And that is all the examples I wanted to go over with U-substitution. Although I am going to make another video that's going to go over go over an FRQ, go over more integration by substitution, because this is a very powerful tool, and we need to know how to do it a lot for our integrals. So thank you for watching.